Good morning, everybody. Today we're going to start chapter 2 in statistics. This chapter deals with the measurements of what's called central tendencies and variations. In the first section, we're looking at frequency distributions for organizing and summarizing data. The reason this is important is because if we talked about big data the other day, and when you first get the data, it's just a bunch of numbers. Doesn't mean much. But once you organize it, you can see patterns, you can see anomalies, you can see a lot of things that you couldn't when the data was just spattered out just as they were given. All right, so what we have to look at when we talk about data, the characteristics of data, I don't know, it's what the parts we're going to be looking at and be most interested in is with center. We call this measures of central tendency. But what that looks for is, okay, we have the data. We're going to see where is the center or the middle of all the data. Okay, yes. But here's something that's important also. When you get the data, to find the center, you can't just look at them as just fold them in half and there you have it. To find the center in any of these, we have to organize them. And that's going to be the focus of today, pretty much, is how to organize our data. The next thing you do is deal with variation or measures of variation. What this looks at is how much or how far the data vary from the center and each other. And these two are the foundations of what we do in statistics. We look at, you've heard of terms like mean, median, mode, variance, and deviation. That's both of these. Mean, median, mode goes here, variance goes here, and we can always put distribution in there, or deviation. The next one is the distribution of the data. What you can look at here is look at the form or nature or shape of the data spread. Well, okay, let's continue this one then. Look at the form or the nature of how you're looking at how they behave, how they interact. Where's all the data looking at? And the form of the data spread mathematically over the range of data values. Typically, what we're looking at here, what we're looking for here, we're looking for a bell shape, or what we call the bell curve. Okay, once you have all these, the center of the variation and distribution looked at, what you can now observe are what we call outliers. These are values that are away from all the other data. Points. Because outliers, again, those could be when somebody answers surveys, they just make up a whole bunch of stuff just to get the free prize. You can see that on the average, everybody's getting over here, and all of a sudden there's one number here. Or the example I showed yesterday was about that curve buster, that one student, if everybody made 30s and 40s and one student made 100, that 100 is an outlier. Why did that person? Then what you do now is try to figure out, why does that outlier exist? Is it human error? Is it a data anomaly, or what? So the outlier could tell us a lot. And lastly is time. Look for any changes in the data over time. Example of that would be, well, right now, if I asked you about artificial intelligence, you'd have an opinion about it. But as time goes on, you learn more about it, you experience it, you've tried a couple of applications of artificial intelligence, and that either strengthens or changes completely your opinions or ideas of what artificial intelligence is all about. So that's the outline of what we're going to do in this chapter. And now in this section here, let's start looking about how we could analyze these numbers, these datas, and what do they mean for us. Right. So the first thing we look at is, what is a frequency distribution? That's the first part, because what we're looking here is just so it says this. The frequency is how many times it occurs. The distribution is how it's spread out. This helps us organize and summarize the data and to better understand the nature of the reasons of the distribution of the data. So this is a whole process. There are actually a couple of different types of processes we can use depending on the type of data we have. When we do an experiment or observation, we collect data. That data could be given to us in many different ways. So usually we just get to say we get a experimental one. So we have numbers. So let's say the numbers are 221, 130, 136. The example they use in the book is during lunchtime at a McDonald's, what is the amount of time that a order is received by the customer, right? So these are times in seconds of lunch at McDonald's. All right, so I'll put a bunch of them in here. So because the more you have, the better your understanding and the better picture you'll get. Here, I'm going to give you a whole bunch of them, and we'll determine what we can do with these in a second. Now, one thing that this doesn't tell us, these different times, is it doesn't tell us how big the order was. It just tells us on when the order was made, when was it delivered to the customer. But what if a customer had a van full of kids? So, I mean, their orders are going to take a little bit longer than the other ones, and those things have to be taken into consideration whenever you do analysis like these. Almost done. As you see, I mean, the more data you have, the more spread out, the more headache it gives you just by looking at them. So that's what we're going to do. We're going to take this data and we're going to figure out how best to organize it. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. That's right. So with this data, we know our N is 50. N is the number of data in our set, in our data set. What we have to do is we're going to look at these data and we have to now put it into some sort of order and organization. Since we notice, the first thing you want to do is find the smallest and the largest data value. The reason for this is that's going to give us our range. It tells us the spread of how far the data points are apart from each other. So looking at this thing, this 77 looks like this is the smallest. So it goes from 77 there's 324 to 324. So we see that's a pretty sizable spread. Because when we do this calculation, this table we're going to create, we can't just put 78, 77, 78, 79, 80. That would take us too much time. So what we have to do here is create what we call a frequency chart. Frequency chart is just that, is we have, it's a little table. And we separate them into different, our data values go here, and the frequency of those data go there, or number of times they occur. So these are called our classes, our frequency class, and that's our frequency. But you see with ours, it's going to be very difficult in that since we have a very far range. Let's see how far that is. So we take 324 minus 77. $247. Let's go ahead and round that up, make them nice numbers. So we'll go, let's say we go from 75 to 325. So that spread is 250. Because yeah, the reason being because 247, that's a weird number, because what we're going to do next is once we found the range, we're going to now decide how many classes do we want. And 250 is a nice round number. So obviously we're going to say decide on the number of classes that you'll have, and then figure out from there. That's this part here, the second side, determining the number of classes to have. That's the only real part that you have any say in. If you put too small of a class, you have a lot of data, these lines. If you have too few, or if each class is very wide, you'll have too few of them, and it won't be an accurate representation of what you're looking at. So ballpark for this one, since it's 250, we could say we want 5 classes. Now, this is the human aspect of it, but there is a mathematical process that you can use. If you don't want to take the time to think about this, what you can do is called the Sturgis guideline for determining the number of classes you're going to have. The formula here is 1 plus the log of n. Remember, n is the number of data points we have, divided by the log of 2. This calculation here will give you an approximate, a pretty good guesstimation of an ideal number of classes to have. All right. But you have to know how many data points you have first. So that's why that one's tough. Other than that, I can see the range. I forgot how many classes I want, and there. Okay, so instead of using 77 to 324, we're going to use the numbers. We're going to round them to our easiest 5 numbers because 5s are easy to work with. All right. Since we know we want 5 classes, the range is 250. Class size is determined by taking the range divided by the number of classes. Because what that's going to do is the range will be, each class will be same size. So 250 divided by 5 equals 50. So that is your class size. It's going, so from in this one, in this one, in this one, the range is going to be 50. Now, the way we do this, the easiest way to do this is, let me go on the next page for this one. We want 5 classes. 1, 2, 3, 4, 5. The first one starts at 75. Remember, our class size we said is 50. So from this number, from 75, if you add 50, that's where the next one's going to start. So 75 plus 50 is 125. And then from this one, add 25 or add 50 to it, we get 175. Add 50 to it, we get 225. And then add 50 to it, we get 275. These, since these are the small numbers, these are what we call the lower class limits. Now, since that one starts at 125, this one goes to 124. This one starts at 175. This one stops at 174. So you see it's a continuation. So that's 224. So this is 274. And our lower bound and our upper bound was, what number we use? 325. So that determines our classes. Okay. Now, we have to take our data and put it in here. Do not say, okay, between 75 and 24, I'm just going to look for them because your eyes will deceive you. What we're going to do first is called tallying. What we're going to do is we're going to use hash marks between 75 and 24. We're just going to pretty much start from this one, start from the first number, and put a hash mark where it goes. So 221 goes here. 130 goes here. 136 goes there. 151, 270, 180, 125, 75, 166. See, now if I stop, if I get disrupted anywhere, I can just count how many marks I have, and that's how many pieces of data I've been through. So I have 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm right here right now. So I go in from there. So 174, 324, 230, 273, 77, 100, 92, 78, 300, 205, 80, 169, 83, 199, 123, 165, 155, 148, 189, 111, 200, 202, 143, 158, 171, 125, 131, 155, 143, 88, 135, 158, 100, 191, 131, 156, 191, 185, 177, 155, 200. All right. So that is our first step. What we've just done with these hash marks is we have organized our data. Because now we could determine how many of our data are in each of these classes. 5, 10, 11, 5, 10, 15, 23, 5, 10, 11, 3, and 2. Here's our first check and balance. If you add up all the frequencies, the sum of all the frequencies should equal n. So 20, 30, 40, 45, 50. We should have 50. Our n should equal 50. And we counted those and we had 50. So that's the first checks and balance that we have. All right, put this away. So here, let's go back here. So here we have our lower class limits. That means these would be the upper class limits. We have a couple more terms with this right here. When we talk about class boundaries, when we talk about class boundaries, what we're looking for here is the number of the numbers that we use to separate each class. that make up, or numbers of each class. So in other words, you notice that we go from 75 to 124, or 125 to 74. But here, we don't want to have, but without any gaps. All right. So what are gaps? Gaps are the space between the upper class limit of one class and the lower class limit of the next class. So between 124 and 125, that's the gap. Because what if we had a number that came in our data points as 124.5 or 124.7? Which group would it be into? It's not bigger than 125. It's too big for 124. So what we have to do is to make them all continuous. To make them all continuous, add the upper class limit of 1 plus the lower class limit of the second one and divide by 2. So it gives us what? 124 plus 125 makes it 149 or 249 divided by 2. So 249 divided by 2 is 124.5. So that is the gap. That's how we fill the gap. So our classes will really go, we notice that from the upper class, it's 124 to 125. So we add 0.5 to the upper classes and subtract 0.5 from the lower classes. Right? So that means in our new table, used to go from, where's my table? It should go from 75 to 124, 125 to 174, 175 to 224, 225 to 275 to 274, 275 to 324. So now here when we add or subtract the 0.5, so we have 74.5 to 124.5. 124.5 to 174.5. 174.5 to 224.5. 224.5 is to 274.5. 324.5. But now you can ask, okay, what if somebody did have 124.5? Which group would it go into? Well, what this says is it's an inequality. It's a range. So if it's a 124.5, it belongs to this one. This one goes all the way up to it. This one goes all the way up to 124.5. If you have 124.5, it starts here. If you have 224.5, it starts here, not there. We just do this so we have a continuation of our entire numeric system. Right? And remember, the class width was from our original, take the second minus the first, or the fourth minus the third. So take any two lower endpoints. So it's lower class value 1 or 2 minus lower class value 1. Or if I'm using this one, I subtract this one minus that one. This one minus that one. That tells me the class width, and they should all be the same size for equal distribution. All right, so that's what we use to create our frequency chart, because now we know that we have in each one of our classes, we know how many we have. This is our frequency. We have, where's that? 11, 23, 11, 3, and 2. We have 50 of them. Because from here, we could do a lot of things. Because now we can use those values as our data points when we do calculations, which will be coming later on in this class. All right, let's look at the next one. So again, when we look at that, the only process that's man-made is determining the number of classes that you have. Well, let me look for my example sheets. Did I not print those out? Oh, here they are. Here's our first example. Well, which is what we did already. Okay, so we did that already. All right, let's see. Let's look at this example. Emergency room visits for injuries from sports and recreation. Table 2-3 lists data from the highest 7 sources of injuries resulting in a visit to hospital ER rooms. In a recent year, based on data from Centers of Disease Control, the activity names are categorical data at the nominal level of measurement, but we can create a frequency distribution as shown. It might be surprising to see that bicycling is at the top of this list, but it doesn't mean that bicycling is the most dangerous of these activities. Many more people bicycle than play football or ride ATVs. So here's what the table looks like. the activity, and the frequency. So the first one we have bicycling, and its frequency of numbers is 26,212. Then we have football, which is at 25,376. Then we have playground at 16,706. Then we have basketball at 13,967. Soccer at 10,436. Baseball at 9,634. And ATVs at 6,337. Okay, so notice from this data, we could also make an analysis of when was this data collected. All of these are usually summer type of activities. Would the numbers be the same in the wintertime? Don't know. So this is what we do. This is a qualitative analysis, because all we did was go and look at the frequencies of each of these activities. These are not classes, these are ranked by the frequencies. But again, from there, we'd have to do further analysis to see exactly what does this stuff really tell us. All right. The next topic we discuss is relative frequency distributions. First off, we look at what is relative frequency. Relative frequency is a running total of frequency values. No, it's not a running total. I don't say that. It's what's the best word I could use here? It's let's say percentage of frequency values relative to n. So that'd be the easiest way to look at it. I mean, it's not a running total, because what we're looking for here is what is the frequency of each class relative to the entire data set. And here's the formula. So relative frequency is calculated this way. The frequency of that class, of whatever class you're looking at, divided by the sum of all frequencies. Because it's relative. I'm using percentage because this is actually, if you look at, that's the formula for it, kind of, it's the part over the total. All we're missing here is the percentage of a class relative frequency is simply the frequency divided by the sum of frequencies times 100. That equals the percent. Also, from here on out in this class, instead of writing the sum of, whatever, I'm simply going to use this symbol. It's a Greek symbol. That's a Greek symbol, sigma. That's Latin, but in Greek it's called summa, which is where we get the word sum from. So it's just the big Greek letter E. All right, so let's go ahead and calculate our relative frequencies for our data. Where's our data? There. Let's also look at not only that, but let's look at the percentage. The class, the frequency, the relative frequency, and the percent. So we have 75 to 124, 125 to 174. I should have put all those separations. Oh well. So we have 11, 23, 11, 3, 2. And we counted all these up. We got 50. So relative frequency, actually, and this, if you look at, because of the symbol I just used, that's the formula I would use. The summation of all the frequencies is equal to n. So the relative frequency formula is the relative frequency, the frequency over the summation of all the frequencies. So the frequency here, 11 divided by 50, 23 divided by 50, 11 divided by 50, 3 divided by 50, and 2 divided by 50. Okay, let me calculate those. Where's my calculator? So 11 divided by 50 is 0.22. So that one's 0.22 as well. 23 divided by 50 is 0.46. 3 divided by 50 is 0.06, and 2 divided by 50 is 0.04. So all we do is multiply those by 100. We get 22%, 46%, 22%, 6%, 4%. Which now what we have to do is here's our second check. Our second check is to, if we add up all the percentages, if it's if it's good, it should equal 100. So 22 is 44. 44 plus 46 is 90, plus it's 100%. So that's the second check that we have. So that's the relative frequency. It tells us how each data is associated relative to all the other ones. So we obviously see that 46% had more weight than the other ones put together. The next frequency you're looking at is called the cumulative frequency distribution. Here we add the frequencies as we go. So each class builds up on the previous one. I should have printed out these values earlier. So we have our class, we have our frequency. So the classes, the frequency, and the cumulative frequency. So we have 11, 23, 11, 3, 2. And here's our classes. The cumulative frequency is you start with the first one. Now, to fill up here, take this plus this. So that makes it 34. This plus this equals 45. This plus this equals 48. Your end result should be n. All right, so again, it's just a different way of analyzing. So what this does is when we do the graphs of these things, we'll see that this graph always goes up. It just shows us how much it goes up with respect to each of these classes. It's just a different way of representing the data itself. Okay, the next one is called a normal distribution. And this is what we talked about the other day also, is what exactly is a normal distribution? A normal distribution is, another name for it is the bell curve. It shows us how an average data set is distributed into percentages, percent categories. So again, the bell curve, if it's normally distributed, it looks like this. It has two conditions that we have to look for. Is it normally distributed? Yes, which means the 50 percentiles right there, 100 is there, and 0 is there. Does it go from low to high and then back down to extremely high? Yes. And then looking at our data set, the one we just had, where was the highest, where was the lowest data points of our distribution? If we looked at it, so we had 11, 23, 11, 3, 2. This is our frequencies. This is our classes. So does our data in our last example, the times of lunch being delivered, is it normally distributed? Well, what we would do here, we could draw a graph. So here we have class A, class B, class C, class D, and class E. This is, instead of writing these numbers here, I'll just refer them to A, B, C, D, E. Here's 5, 10, 15, 20, 25. So the first one had 11. And we'll talk about graphs in another section. So that one had just a little bit more than 10, so it's about 11. The next one had 23. So it's halfway between 20 and 25. So this is 11. This is 23. This is also 11. Then 3. Then 2. So if we were going to draw a graph on this one, our graph would look like that. So we see that our data is not normally distributed. What we're going to talk about this in the next section is this. We're talking about skewness. And since it's farther to the left, this is skewed right. Don't worry about now why it's over here. Why is it right? I'll show you. We'll talk about that tomorrow, or our next class. All right, let's look at examples here. Upon examination of measured pulse rates from 2,219 adults included in the National Health and Examination Survey, the last digits of the recorded pulse rates are indicated in the frequency distribution. For those last digits are shown in table 2.7. Let me see if I have 2.7 here. Yes, I do. And here it is. last digit, and here's the frequency. Instead of writing the frequency, you could just put the letter F, since that's going to be frequency for us from here on out. So 0, 1, 2. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are our last ones that we have. 455, 0, 461, 0, 479, 0, 425, 0, 399, 0. All the last digits are even numbers. If the pulse rates are counted for 1 full minute, they would surely be larger numbers and ending in odd digits. What happened here? So this is what you would look at to see, okay, now why is this thing not working right? But remember, these are pulse rates. So if you saw this, it's okay, all the pulse rates are even integers or even numbers. Why? Well, is that it could be that's the way the machine's calibrated. It rounds up. Or it takes an average of how many pulses in this minute to this one, add those two together, divide by 2. And when you divide by 2, you get even numbers. So again, all this stuff, is it machine error or is it human error? That's what you'd have to look at next. All right. How about example 4? In example 4, we're exploring the data, and what are the gaps going to tell us? In table 2.8, which is here, if I left it here, the frequency distribution of the weights of randomly selected pennies. Examination of the frequencies reveal a large gap between the lightest pennies and the heaviest pennies. This suggests that we have 2 different populations. Pennies before 1983 are 95% copper and 5% zinc, and pennies after 83 are 2% copper and 97.5% zinc, which explains the large gap between the largest and heaviest pennies. So, what happened here? In the middle, because of the composition of the pennies, that is a logical explanation. So what we're doing here is combining 2 or more relative frequencies. We have one here and we have one here. So we have before 1983 and after 1983. Instead of having 2 separate charts, we could put them on one, and then it'd be easier to come up with a conclusion that way. And the last one. Comparing McDonald's to Dunkin' Donuts. Table 2.9 shows relative frequency distributions for the drive-through lunch services. Because the dramatic differences in their menus, we might expect service times to be very different. By comparing the relative frequencies, the percentages, we see that there are major differences in that Dunkin' Donuts service times appears to be lower than those of McDonald's. This is not too surprising, given that many of the Dunkin' Donuts orders are probably for coffee and donuts. Which is exactly what it is because Dunkin' Donuts, they created their business plan to service the average worker who at the time when they first developed, they didn't have that much time for lunch. They were on a snack break, which Dunkin' Donuts pretty much invented the term snack break. So all their entire business plan was, you didn't want the customer to spend more than 10 minutes in your restaurant, because the longer they stay there, the less people can go through, the less traffic can go through. So that's how come their coffee and donuts are the big sellers. In McDonald's, you have everything from full meals, lunch, pretty much dinner, which takes lots of time to eat. And because of those, each order is made differently. Hamburgers take a certain amount of time to cook, French fries. So yeah, these should be more time spent preparing. All right, everybody. So that does it for that section. We'll look at histograms next. Thank you. Have a great weekend.